The interstellar comet 3I Atlas just passed its closest point to the Sun, and the latest images are showing something that has planetary scientists in heated debate. This thing's tail is still growing even as it moves away from the Sun and should be cooling down. We're seeing jets maintaining perfect alignment across 620,000 miles, despite the object rotating every 16 hours, which is like watching a garden sprinkler create a straight line while it spins in circles. The European Space Agency just achieved something unprecedented. They tracked this object from Mars orbit and improved our trajectory predictions by a factor of 10. And what that data reveals is forcing scientists to reconsider how we calculate comet masses. But here's the part that's really got everyone talking. Images captured on November 11th show this object is still in one piece, yet the math says it's losing 50 billion tons of material while only weighing 33 billion tons total. That's like pouring 10 gallons of water from a 5-gallon bucket, and nobody can agree on how that's physically possible. Stephen Desch and other experts point out that Loeb's statistical argument has a fundamental flaw. Yes, the trajectory is unusual, but Loeb is calculating probabilities after the fact, after we already know what the trajectory is. That's a classic statistical fallacy. It's like shuffling a deck of cards, dealing a specific hand, and then calculating that the probability of getting that exact hand was 1 in billions. Well, yes, but some hand had to come up. The question isn't whether this specific trajectory is unlikely, it's whether there's any reason to think it was deliberately chosen rather than random. Desch also notes that saying a comet in the ecliptic passes close to some planets, but is also anomalous for not being close to others is having it both ways. With logic like that, every comet could be called anomalous. But let's move past the trajectory debate and talk about what happened as 3I Atlas got closer to the Sun, because this is where things get genuinely interesting. Back in May 2025, before the object was even officially discovered, NASA's Transiting Exoplanet Survey satellite happened to catch it on camera. Tests tracked 3I Atlas for about a month as it moved through Jupiter's orbit, and astronomers noticed something unusual. The object was brightening much faster than expected. They calculated it should brighten by a factor of about 1.5 times as it approached the Sun. Instead, it brightened by a factor of 5. This told them immediately that 3I Atlas wasn't a solid rock. It was a comet forming a coma, that fuzzy cloud of gas and dust that surrounds an active comet. But here's what was weird. It was forming that coma way too early. 3I Atlas was still beyond Jupiter's orbit, over 465 million miles from the Sun. At that distance, temperatures are around minus 280 degrees Fahrenheit. Most comets from our solar system don't start forming their comas until they get much closer, around 280 to 370 million miles from the Sun, because that's when water ice, the main component of most comets, starts to sublimate. So why was 3I Atlas already active so far out? When astronomers analyzed the spectrum of light coming from the coma, they found it was dominated by carbon dioxide gas, not water vapor. The ratio was about 8 parts, CO 2 to 1 part water, basically the inverse of what we see in typical solar system comets, which are usually 8 parts water to 1 part CO2. Now, Loeb has called this an anomaly, but planetary scientists say this isn't actually that strange. Carbon dioxide sublimates at much lower temperatures than water ice. That's exactly what was happening with 3I Atlas way out in the cold. The CO2 ice was sublimating at temperatures that would keep water ice frozen solid. The fact that the ratio is inverted just tells us that 3I Atlas formed in a different kind of solar system than ours, one where CO2 was more abundant than water during the comet's formation. That's not evidence of anything artificial, it's evidence of diversity in planetary systems across the galaxy. But then something interesting happened. As 3I Atlas got closer to the Sun in late September, passing through Mars's orbit at about 140 million miles out, it suddenly started releasing massive amounts of water vapor. The ratio of CO2 to water flipped. Now it was mostly water with just a little CO2. This makes perfect sense. The outer layers of CO2 ice had sublimated away. It's like peeling an onion, layer by layer. Now let's talk about what happened after perihelion. 3I Atlas reached perihelion on October 29, 2025, at a distance of about 130 million miles. That's roughly the distance between the Sun and Mars. For comparison, Earth orbits at 93 million miles from the Sun. At perihelion, the Sun's heat should have been most intense, causing maximum outgassing and activity. Then the object passed behind the Sun from our perspective, and we'd lost sight of it for about 2 weeks. When it emerged in early November, astronomers expected to see it cooling down, becoming less active, its tail shrinking as it moved farther from the Sun's heat. That's what every comet does, it's basic physics. But that's not what happened. Images captured on November 15, 2025, by Tirasak Taluang using a telescope in Thailand showed something surprising. The tail was still growing. Not only that, but the object was still displaying a prominent anti-tail, a jet of material pointing toward the Sun, along with 2 regular tails pointing away from the Sun. Now, Loeb has called this anti-tail anomalous, but here's what planetary scientists want you to know. Anti-tails aren't that unusual. They've been observed and explained for 50 years. An anti-tail can form when large dust particles around 100 micrometers in diameter are released from a comet. These particles are about 1 million times more massive than the typical micrometer-scale dust that creates normal comet tails. Because these giant particles have a much lower surface area-to-mass ratio, they're not pushed away from the Sun by radiation pressure as effectively as smaller particles. They move more slowly, and from certain viewing angles, they can appear to point toward the Sun. It's often an optical illusion based on geometry, but even when it's real, it's not mysterious, it's just physics. Another explanation proposed by Eric Quito and Loeb himself is that the anti-tail could be made of ice fragments rather than refractory dust. These fragments would sublimate before they had a chance to turn around and form a traditional tail. Either way, there are natural explanations that don't require anything exotic. But here's where the story gets more complex. Images captured on November 8th and 9th showed something more dramatic. Jets of material stretching 620,000 miles toward the Sun and 1.86 million miles away from the Sun. For reference, the distance from Earth to the Moon is 240,000 miles. These jets are stretching nearly 8 times farther than that. And here's what's puzzling. Back in July and August, astronomers measured 3 I-Atlas's rotation period at 16.16 hours. If an object is spinning every 16 hours and shooting out jets of material, those jets should be smeared out in a spiral pattern as the object rotates. It's like a lawn sprinkler. As it spins, the water creates a circular pattern. But the jets from 3I Atlas appear to be tightly columnated, narrow and focused, maintaining their orientation across hundreds of thousands of miles. Loeb calls this the 12th anomaly and suggests it's evidence that the jets might not be caused by normal sublimation. However, there are natural explanations for this too. One possibility is that the rotation has slowed down significantly since July. Outgassing can act like a brake on a comet's rotation, especially if the jets are asymmetric. Another possibility is that the jets are only active when specific parts of the surface are illuminated by the Sun at certain angles. Imagine you have ice pockets in deep valleys on the comet's surface, surrounded by mountains that shadow them. Those pockets would only be exposed to direct sunlight when the Sun is at exactly the right angle. This would create pulsating outflows with a period of 16 hours, but the jets would all point in roughly the same direction, toward the Sun, because the ice quickly cools when it's not illuminated. This wouldn't explain jets pointing away from the Sun, but those could be explained by a different mechanism, perhaps the evaporated trail of fragments that were ejected from the main nucleus. And that brings us to the biggest question of all. Has 3I Atlas broken apart? Loeb calculated the mass loss from 3I Atlas based on the size and density of the jets. To push against the solar wind and stay coherent for 620,000 miles, the jets must be incredibly dense. His estimate, about 50 billion tons of material per month. But by tracking how the object moves and how the Sun's gravity affects it, scientists calculated that 3I Atlas weighs around 33 billion tons total. You see the problem. It can't lose 50 billion tons if it only weighs 33 billion tons. That's physically impossible. The most obvious explanation is fragmentation. If the object has shattered into hundreds or thousands of pieces, each fragment would have its own surface area exposed to sunlight, creating its own jets. The total mass loss from all those fragments combined could easily exceed the original mass of the intact object. We've seen this before with comets in our solar system. Here's the catch. On November 11, 2025, astronomers David Jewett and Jane Liu used the Nordic Optical Telescope in the Canary Islands to capture new images of 3I Atlas. And what they saw was surprising. The object appeared to still be a single intact body. There was no obvious evidence of fragmentation. The object showed a prominent elongation in its coma, pointing toward the sun at a position angle of 106 degrees, close to the actual sunward direction of 115 degrees. So we have this paradox. The object appears intact, but the math says it's losing more mass than it weighs. Now, here's where planetary scientists push back on Loeb's calculations. They point out that his estimate of the non-gravitational acceleration, the force from outgassing that changes the comet's trajectory, is based on measurements that were unbelievably exact, down to 1 part in 10 billion. But in reality, they were only accurate to about 1 part in 10 million. In other words, the data was 1,000 times less precise than Loeb assumed. This is a huge deal because if the measurements aren't as precise as Loeb thought, then his calculation of how much mass is being lost could be way off. The comet might not be losing nearly as much material as he calculated, which would resolve the paradox entirely. There's another issue with Loeb's mass loss calculation. He assumes that the jets need to be incredibly dense to push against the solar wind. But what if the jets are made mostly of gas with very little dust? Gas is much lighter than dust, so the mass loss could be much smaller than Loeb calculated, while still producing visible jets. Or what if the object is much heavier than we think? Our estimates of its size and density are based on how much sunlight it reflects, and how the sun's gravity affects it. If those estimates are off, and they could be, then the object might weigh more than 33 billion tons, which would resolve the paradox. Now, let's talk about the European Space Agency's contribution to this story, because this is actually a really big deal. ESA used data from their ExoMars Trace Gas Orbiter to track 3I Atlas from Mars orbit. By observing from a completely different location than Earth-based telescopes, they got a different viewing angle, which allowed them to triangulate the object's position much more precisely. This improved the accuracy of 3I Atlas's predicted trajectory by a factor of 10. That's huge. And this was actually the first time that astrometric measurements from a spacecraft orbiting another planet have been officially submitted and accepted into the Minor Planet Center database. What this proves is that we can use our Mars orbiters to track potentially hazardous objects with much greater precision than Earth-based observations alone. It's a valuable test case for planetary defense, even though 3I Atlas doesn't pose any danger to Earth. But here's what ESA's data also revealed. 3I Atlas's trajectory is very consistent, with very little deviation or wobble. For a natural object that's supposedly fragmenting and losing mass asymmetrically, you'd expect more perturbations in its orbit. The fact that it's moving so smoothly is interesting, though not necessarily anomalous. Now, the images everyone's been waiting for are the ones from NASA's Mars Reconnaissance Orbiter. On October 2nd and 3rd, 2025, 3I Atlas passed within 18 million miles of Mars, about 75 times closer than it ever got to Earth. The orbiter's high-rise camera captured multiple images with a spatial resolution of about 19 miles per pixel. That's good enough to tell whether we're looking at a single solid object or multiple fragments. These images were supposed to be released in October, but they got held up due to bureaucratic issues at NASA related to a government shutdown. As of mid-November, sources indicated the images would be released within a few days, but now we still haven't seen them. These images are crucial because they'll answer the fundamental question: is 3I Atlas intact, or has it broken apart? If it's intact, then we need to figure out why the mass loss calculations are wrong. If it's broken apart, then the mystery is solved. Fragmentation explains everything. The truth is, we don't have all the data yet. Those high-rise images could be released any day now. On December 19th, 2025, 3I Atlas will make its closest approach to Earth at about 130 million miles, giving us another opportunity for detailed observations. And on March 16th, 2026, it will pass within 33 million miles of Jupiter, where NASA's Juno probe will have one final chance to capture images before 3I Atlas leaves our solar system forever. So what's the bottom line? Here's what we know for certain. 3I Atlas is an interstellar comet that formed in a different solar system with different chemistry than ours. It's showing us that not all comets are created equal, and that the conditions in other star systems can produce objects with very different compositions and behaviors than what we're used to. The extreme negative polarization of light reflecting off its coma, the inverted ratio of CO2 to water, the early formation of its coma, the sudden appearance of water vapor and iron as it heated up, all of these things tell us that 3I Atlas is different. But different doesn't mean artificial. It just means we're seeing the natural diversity of objects in our galaxy. As for the mass loss paradox and the tightly collimated jets, we'll have to wait for more data. The high-rise images will tell us whether fragmentation is the answer. The December observations will show us whether the tail continues growing and whether the jets remain active. And the March flyby of Jupiter will give us one last look before this cosmic messenger disappears into the darkness. Drop a comment below and let me know. Do you think the mass loss paradox will be resolved by fragmentation? Or is there something else going on? And if you know someone who'd be fascinated by this cosmic mystery and the scientific process behind understanding it, share this video with them. Thanks for watching, and I'll see you in the next one.